Okay, so today we will discuss some of the application of the operational amplifier, that means inverting amplifier, non-inverting amplifier, what was the gain of the inverting amplifier, what is the gain of non-inverting amplifier, adder, subtractor, like that. Okay, so first application, these are all the linear application of the operational amplifier. Linear application means the relationship between the output voltage and the input voltage that has been applied to the operational amplifier, the relationship between them is linear. So the first application of the operational amplifier is a linear application of the operational amplifier is the inverting amplifier. So first one is your inverting amplifier. Okay, so first I am just drawing the circuit diagram of the inverting amplifier. So this is the 1 minute. Negative, positive has been grounded. Okay, we have given input to the negative terminal because this is the inverting amplifier. So input has been given as V1 and there is a resistance R1 and there is a feedback resistance RF. Okay, this is the very simple application of the operational amplifier. So this is your V0. Okay, and the current flowing through the I1 and current flowing through this is IF. I am just drawing this. So this point and this point. So we have used first one, this figure shows the circuit diagram of an inverting amplifier. So this is the circuit diagram of an inverting amplifier using the operational amplifier. Then the circuit input voltage is applied to the inverting terminal. You can see that the input voltage, this is the input voltage that has been applied to the inverting terminal through a series resistance. The series resistance is R1. Okay, and the output voltage V0 is fed back to the inverting terminal through the feedback resistance RF. Now you can see this is the feedback resistance RF through which output voltage is being fed back to the input. So this is a clear cut indication of the negative feedback. Okay, so the non-inverting terminal of the operational amplifier is grounded, and the third point is the non-inverting terminal, this terminal of the operational amplifier is grounded. Okay, now for the circuit analysis, assume that the gain of the operational amplifier is infinite. That means here we are assuming that ideal op-amp. Okay, so the open loop gain of the operational amplifier is infinite, input resistance is infinite, output resistance is 0. So for that purpose, the operational amplifier, we can use the virtual ground concept. So virtual ground concept can be used in this operational amplifier. Now as we know that the ideal case input resistance, we have assumed that the input resistance of this operational amplifier is infinite. So as the input resistance is infinite, the operational amplifier does not draw any kind of current, that we have also discussed previously. So this current is actually 0 ampere current. Okay, so whatever current is flowing through this I1, this current I1 is exactly equal to your IF. Okay, so I1 is nothing but, due to the virtual ground concept, this potential is 0 volt, and due to the same virtual ground concept, this potential is also 0 volt. So whatever what is the value of current I1 equal to V1 minus 0 divided by R1. Okay, or you can say I1. Okay, so virtual count has been applied, so I1 equal to V1 minus 0 divided by R1. So this is the I1, and this current is also equal to the IF. So what is the value of IF? IF is nothing but 0, current is flowing through 0 volt to V0. We have assumed in that direction, so that's why 0 minus V0 divided by RF. So this is also equal to 0 minus V0 output voltage divided by RF. Okay, so this is the current flowing through the feedback resistance IF. So this is nothing but your IF. Okay, and if we just solve this, I1 equal to IF, so I1 equal to IF, we know that I1 equal to IF. So if we just solve this, V1 by R1 equal to V minus V0 divided by RF, minus V0 divided by RF. So our gain is V0 divided by V1 equal to nothing but minus RF divided by R1. Okay, so this is the gain of this non-inverting amplifier. So this the overall loop gain of the amplifier and its negative value indicates as the phase inversion of the output signal. Phase inversion means the output voltage, whatever the value of the output voltage, that is 180 degree out of phase with the 180 degree out of phase with the input voltage. Okay, so whatever value of the output voltage, that is 180 degree out of phase with the input signal. Okay, so that is the characteristics of the inverting amplifier. Now this circuit diagram can be this circuit can be used for the sign changer when the gain is 1. Okay, so when the gain is 1, suppose your gain is 1, so V0 divided by V1 equal to -1. That means whatever the output voltage, input voltage, the output voltage just the opposite of that, so it can be used as a sign changer. Okay, so this can be also be used as a sign changer very easily. Okay, so hope you understand this. So moving forward, we will next discuss the non-inverting amplifier. Okay, so next is non-inverting amplifier. So in the case of the non-inverting amplifier, first in the previous case, likewise in the previous case, we will first draw the circuit diagram, next we discuss the circuit diagram. Okay, so just drawing the circuit diagram. So this is your negative, this is your positive terminal. So as this is the non-inverting meant we are giving the input to the non-inverting terminal. So this is your input, this input we may consider as V1, and this terminal there is a resistance. Previously there is a resistance and the input is there, but here now this is grounded. This resistance is R1 and there is a feedback resistance, and this feedback resistance is RF, and this is the output voltage V0. Okay, so this is the circuit diagram. This is the circuit diagram for the non-inverting amplifier. Okay, now in this circuit diagram, the input voltage is applied to the non-inverting terminal of the amplifier. Okay, the feedback resistance RF is connected between the output voltage terminal and the inverting input terminal. Okay, you can see the circuit diagram, and the resistance R1 is connected between the inverting terminal and the ground. This resistance R1 is connected between the inverting terminal and the ground. Okay, now sorry, the potential here the potential, 1 minute. So likewise in the previous case, what I have considered, here also we have considered the ideal Opamp. Okay, so likewise in the previous case we have also considered here the ideal Opamp. Now in the case of the ideal Opamp, you can consider the Opamp draws no current. That means this current drawn by the operational amplifier is 0 ampere, and we can use the virtual ground concept very easily due to the open loop gain of the Opamp is infinite, and in addition to that, a negative feedback is being applied to the non-inverting terminal, sorry, inverting terminal. Okay, so as we applied the virtual ground concept, then you can easily see that this potential is V1 also. So this potential at this point, okay, so potential at this point is also V1. Okay, so the current, this current we have also assumed this current as I1 and this current as IF. So the same concept being applied here. So I1 is nothing but 0 minus V1. This potential is V1, so 0 minus V1 divided by R1. This is your I1, and IF is equal to V1 minus V0 divided by RF. So this is V1 minus V0 divided by RF. So V1 minus V0 divided by RF. And also as the Opamp is ideal, so the Opamp draws no in any amount of current, does not draw any amount of current. That means the 0 ampere current is drawn by the operational amplifier. So this I1 is exactly equal to IF. Likewise in the previous case, this I1 is exactly equal to IF. So equating both these two, minus V1 by R1, so minus V1 divided by R1 is equal to V1 minus V0 divided by RF. Okay, so V0 by RF, this coming here equal to V1 by RF, V1 by R1. Okay, so V0 by RF, 1 by RF, okay, 1 by RF plus 1 by R1. So V0 divided by RF equal to 1 by RF, 1 by R1. Okay, so V0 divided by RF equal to here it is RF R1 and it is R1 plus RF into V1. So RF is being cancelled, so your V0 is nothing but R1, so 1 plus RF divided by R1 into V1. Okay, so this is the equation for the output voltage in the case of the non-inverting amplifier. So the gain of the non-inverting amplifier, from the above expression you can see that the gain of the non-inverting amplifier is 1 plus RF by R1. So this is the relationship between the input and the output voltages. Now here in this case, in the non-inverting amplifier, you can say whatever the magnitude of the output voltage, that means the sign magnitude, and between V0 and V1 the magnitude, sign magnitude is same. So you can say there is a 0 degree phase shift between the output voltage and the input voltage in the case of the non-inverting amplifier. But in the case of the inverting amplifier, we have seen that the relationship between the output voltages and the input voltages is 180 degree out of phase. That means if the V0 is positive, V1 is negative. If V1 is negative positive, V0 is negative. That is the case here. If V0 is positive, V1 is positive, so there is no phase shift. So there is 0 degree phase shift between these two. Okay, so this is all about the non-inverting amplifier. So we have also discussed the inverting amplifier, non-inverting amplifier. Next is your very small application, that is called the voltage follower. Now what is voltage follower? Now in the voltage follower circuit, this is the application of the non-inverting amplifier. Now in the case of the non-inverting amplifier, suppose this is your non-inverting amplifier. So we have given the input here. Suppose the input is given here is Vin. Okay, and what we make this is sorted like this. This is short circuited. So this is your circuit. So this is clearly a non-inverting amplifier with this RF is being short circuited. Okay, so what is the output voltage in this case? So the output voltage in this case is nothing but 1 plus RF by R1. So RF here is 0 divided by R1, because the feedback resistance is short circuited, so into V1. So V0 is equal to V1. So whatever value of the input voltages that has been appeared at the output voltages. Okay, so that's why this circuit is called the voltage follower circuit. Okay, so next one is your adder circuit. Adder or summing amplifier, you can say adder or summing amplifier. Now this circuit, I'm just drawing the circuit first. So this is your circuit. This is negative, this is positive, and here this is being grounded, and 2 input is being applied. So this is the feedback resistance, this is your V0, this is your RF, and 2 input is being applied, because 2 input is going to be added. From the name it implies that it is added, so whatever input is being applied at the input, that supposed to be added at the output. Okay, that is the meaning of the adder or the summing amplifier. So this 2 input is being coming from the 2 resistance. Okay, you can connect as many input as you want. So this is V1, this is V2, this is R1, this is R2. Okay, so this is the 2 input V1 and V2, and this is the 2 resistance R1 and R2. And obviously current flowing through this is I1, and current flowing through this is I2, and current flowing through this is RF. Same concept is being applied. So just look into the circuit. So this is nothing but an extension of the inverting amplifier. Okay, so I1, what is the value? And the same previously same concept is being applied. That means the op-amp is ideal, so that you can use the virtual gun concept. That means the gain of the open loop gain of the operational amplifier is infinite, input resistance is infinite, and the output resistance is 0, and the negative feedback is being applied. Okay, you can see that the negative output is feedback to the negative portion. So the clearly this is the example of the negative feedback. So that's why you can very much easily apply the concept of the virtual ground. So in the concept of the virtual ground, you can apply the virtual ground concept. So this potential is 0 volt, so this potential is obviously at 0 volt. Okay, so this is the concept of virtual ground. So what is the value of I1? Your I1 is nothing but, what is the value of I1? So I1 is nothing but V1 minus 0 divided by R1. So V1 divided by R1, so I1 is nothing but V1 divided by R1, and I2 is nothing but V2 divided by R2, and IF is nothing but 0 minus V0, that means minus V0 divided by RF. So these two current is entering here, and this current is here IF. So I1 plus I2 equal to IF. This is a clear thing. That means KCL, whatever current is entering at this node is flowing out is IF. So I1 plus I2 equal to IF. So V1 plus R1, V1 divided by R1 plus V2 divided by R2 equal to minus V0 divided by RF. So minus V0 divided by RF. Okay, so this is the equation, and from that equation V0 equal to minus RF by R1 V1 plus RF by R2 into V2. So this is the expression for the summing amplifier. Okay, now this is something at the summing amplifier one must be familiar to see the output as like this. That means the summing means sum. So V0 might be equal to the summation of V1 plus V2, but that is connected to inverting input, so that must be a negative sign B2 before there. Okay, so if we make RF and R1 and R2 both 3 are equal, that means R1 equal to R2 equal to RF. This is the case. If this is the case, then this will be cancelled out. So your V0 is nothing but the summation of V1 plus V2. Okay, but a negative sign will come here, because this is a clear extension of the inverting amplifier. But you can eliminate this just connecting this to a inverting amplifier. If you connect again inverting amplifier, this V0 as an input, then we can eliminate this negative sign. That means negative will become positive. So we need again extra amplifier. Okay, so that your expression will something look like this: V0 equal to V1 plus V2. Okay, so extra inverting amplifier, after that you can get that output like this: V0 equal to V1 plus V2, a very smoothing output. Okay, so next is your difference amplifier, subtractor or the difference amplifier. Now in the case of the subtractor of the difference amplifier, there is a two circuit with the two op-amp or with a one op-amp. So today we will discuss with the one op-amp circuit. So subtractor or the difference amplifier with one op-amp. So this is the difference amplifier, okay, with one op-amp. So one op-amp means this is the circuit. So circuit is something this is negative, this is positive, okay. So this is a voltage V1 and this is a resistance R2, okay, and this is a voltage V1, this is a resistance R1, this is a resistance R2, and this is a voltage V2, this is a voltage V2, this is a resistance R2, and this will be your feedback resistance RF, okay. So the current flowing through, current direction in that case, the current flowing through this is your I1 and this is your I2, this current, as the op-amp draws no current, okay. So this is your IF, okay. So typical differential amplifier with on operational amplifier in the shown in the figure. So assume the differential voltage between the inverting and the non-inverting terminals is 0. That means VD is equal to 0. So VA equal to VB. So nodal equation, it means this equation. Suppose this point is VA. This is your VA and this is your VB, okay. So the node equation at node B, we are first considering this node B. This is your node B. So node equation as node B is VA minus V1 minus VB divided by R1 VB minus 0, okay. So VB minus 0, this is your VB, this is 0 divided by R2, okay. So you can see this equation, this is V1, this is the node B. So the potential at node B we have considered as VB, and this current is nothing but V1 minus VB divided by R1, and this is VB minus 0 divided by R2, okay. So V1 minus R1, so V1 divided by R1, here you can solve V1 divided by R1, you can solve it. V1 divided by R1 is nothing but VB into R1 plus R2 divided by R1 R2. You can solve on your own, then you get this equation, okay. So V1 by R1 equal to VB into R1 plus R2 into R1 R2. VB is the node, this node potential, okay. So VB is nothing but, okay, so your VB is nothing but this point potential is nothing but V1 into R1 will got cancelled, so R2 divided by R1 divided plus R2, okay. So this is the VB, okay. So this is your VB, but as the concept of the virtual ground, so this VA, this point potential VA is also be equal to this VB, okay. So this VA is also be equal to V1 into R2 divided by R1 plus R2, okay, as VA equal to VB, as VA equal to VB due to the virtual ground, okay. So I1 equal to IF, next I1 equal to IF, you can see this I1 is equal to IF, this point potential is known, so V2 minus VA equal to VA minus V0 divided by RF, the same thing. So V2 minus VA, we can solve this by V2 minus VA divided by R1, okay, sorry, R2 equal to VA minus V0 divided by RF. So VA minus V0 divided by RF, okay, and just put I am not solving all this, you can solve your own. Just put here this VA, this equation VA, put here, okay, and solve on your own. Then ultimately you will get that value. V0 will be equal to R2 divided by R1. That means RF final value will be something different. That means V0 will be 1 plus RF divided by R1, 1 plus RF divided by R1 into R2 divided by R1 plus R2 into V1 minus RF by R1 into V2. Okay, so this is the equation after putting this. Okay, I am not solving this, you just solve on your own, you will get the same value. Next put RF equal to R2. Next put RF equal to R2, this voltage, this resistance equal to this resistance. Okay, if you put this resistance, then what you will get, you will get V0 equal to, you will get V0 equal to R2 divided by R1, R2 divided by R1 into V1 minus V2, V1 minus V2. Okay, so this circuit is very useful to detect a very small difference between the two signal. Then you can see V0 is almost proportional to, linearly proportional to V1 minus V2. Now if one can just make all the resistance equal, so V0 equal to V1 minus V2. Okay, so this circuit is very useful. As they said, the application, this circuit is very useful to detect very small difference between the two signal, as the gain can be considered large value. For example, when R2 equal to 100 kilo ohm and R1 equal to 1 kilo ohm, then the gain is 100, so the difference will be amplified by 100 times. So this difference, whatever be the small difference, this circuit can be useful to detect the very small difference between the input. Okay, so that is the application of this. Thank you.